This video looks at an example of projectile motion. This is in section 3.13.4 of your book. I actually call it 13.4 part 1. So there are other things in that section. The only thing we're going to look at is projectile motion, at least for now. And this is an application of integration of vector functions. You considered falling body problems in single variable calculus. So that would be something where maybe you had some sort of cliff or something and an object was thrown up and then dropped with with gravity as the only force on it, and you could figure out its position function, you could figure out when it would hit the ground and all that. But that was only one-dimensional motion. We could only do what's called rectilinear motion, up and down or left and right. Here, now that we have multiple variables, we're going to consider an object that is thrown and lands somewhere, some sort of projectile motion. You may have done this in physics, and your book does this a little bit differently. They kind of derive all the formulas ahead of time, and then they just turn this into a use of formula section. You can do that. You can use what you know from physics. But I really like to do these problems from the basic principles, just because I think it's really interesting what you can figure out just with one basic principle, essentially. So here we have a projectile fired with a muzzle speed of 150 meters per second at an angle of 45 degrees from a position 10 meters above the ground level. So we've got something like this going on, 10 meters above the ground level. We have some sort of gun or something, and we have 45 degrees to horizontal. So this angle right here is 45 degrees. 150 meters per second, that would be the initial velocity. So you could think of this initial vector here as having a magnitude of 150 meters per second. And so it fires this object, and the question is, where does it hit the ground and with what speed? So these problems like this can all be done from one basic principle, and that is once that object is fired, the only force acting on it is acceleration due to gravity, and that acts straight downward. So that acceleration would be minus the gravitational constant in the y direction, so times j. And so we start each of these problems with acceleration equals minus the acceleration constant. So we're using meters in this case, so 9.8 j. We use in here that g equals 9.8 or 32. That's seconds squared. Meters per second squared. So that's the acceleration vector. If we integrate that, we get the velocity vector. So velocity equals the integral of acceleration. So that's going to be negative 9.8 t times j plus a constant of integration. I'll just call it c for right now. Now to find that constant of integration, we use some sort of initial conditions. And so if we looked at the velocity at time 0, if I put 0 into this equation, then I just get that constant right there. And so because of that, then we often just call that constant v sub 0 initial velocity vector. So similar to what we do with the rectilinear motion, when we integrate this, we typically just go ahead and write this constant right here as v sub 0. So that constant of integration will always be the initial velocity vector. So we need to find that initial velocity. And we can do that by the fact that we know that this 150 meters per second, that is the magnitude of this initial velocity, and 45 degrees is the direction. And so putting that magnitude and direction into component form, then we have magnitude times the cosine of the angle and magnitude times the sine of the angle. So that's going to be 75 radical 2, 75 radical 2. So that's our initial velocity vector. And so that goes right in up here. V equals negative 9.8 t times j plus our initial velocity vector. And I'm going to go ahead and write that in ij form so that I be consistent with what I started up here. We can do this all in this form or all in this form, but since I started like this, let me just go ahead and continue with i's and j's. So 75 square root of 2i plus 75 square root of 2j. So this is my velocity vector function. I have 75 square root of 2i, and then if I combine my j's, I have 75 square root of 2 minus 9.8 t times j. I want the position function, so to get the position function, I just integrate the velocity function. So if I do that, I'm going to get 75 square root of 2 t times I plus 75 square root of 2 t minus 9.8 t squared over 2, so 4.9 t squared, j, and all of this times some sort of constant of integration, not the same constant. In fact, using the same sort of explanation that I did here, this constant right here turns out to be the initial position vector, because this is the position at any time. If we put in time 0, this is all 0, this is all 0, and this is what's left. So this constant of integration here is going to end up being the initial position. So we often just write it as R0. That's the initial position. So over here, R0, which I'll call initial position. If we look at where we are initially, we are at 0, 10. So the initial position is 0, 10, just 10 vertically, which I can write as 10 times j. And so that means that R is going to be 75 square roots of 2t times I plus 75 square roots of 2t minus 4.9 t squared times j plus that R sub 0, which is 10j. And combining that in with the other j components, 75 square roots of 2t times I plus 75 square roots of 2t minus 4.9 t squared plus 10 times j. So this is our position vector at any given time. Notice this I component, that would be our horizontal, and this is our vertical. So at some given time here, so R at some time would point to where we are. The X component here would give me the horizontal component of that position, and the y component here would give me the vertical. So we can think of breaking down that position into horizontal and vertical. Once we have that position function, there are a number of questions that you may be asked. This particular one says, where does the projectile hit the ground? So where does it hit the ground? So it hits the ground here, when the y component of the vector is 0. Okay, so it hits the ground when 75 square root of 2t minus 4.9t squared plus 10 equals 0. So that's the time that it hits the ground. Sometimes we call that the time of impact. So if we want to know when it hits the ground, we can just solve this equation. It's a quadratic equation, so if we use the quadratic formula, I'll let you do the computation. We get two values for t. The positive one is approximately 21.74 seconds. So that's when it hits the ground. That's the time of impact. Where does it hit the ground? What we want to know is this point right here. That's the x component of the time of impact. So where it hits the ground, so when and where hits the ground is the x component at the time of impact. And so that's going to be 75 square roots of 2 times the time of impact, which is approximately, that notation in case you didn't see that, I just wrote that for time of impact. That's 75 square roots of 2 approximately times 21.74. So that is approximately 2306 meters. So over here, that distance, it lands 2306 meters. So we sometimes call that the range of the projectile. The other question is the speed, and speed is just the magnitude of the velocity vector. So at the time of impact, here's the velocity vector up here. So we'll just put in our time of impact and then take the magnitude. So that's going to be v at the time of impact. So time of impact, which is approximately equal to v at 21.74. And that's approximately 151 meters per second. Okay, so this example is worked in the book, but they do it using the formulas that they derive ahead of time. I really like to do it this way myself, because I think it's pretty amazing that from this one fact right here, that we can get all this information about this projectile. And there's other questions that you'll be asked, like, what's the highest it goes and things of that nature, but all based on this one fact and using integration of vector functions.